recorded, and if you want to say something, you can say. Otherwise, what you can do is maybe you can raise your hand and then you say it. Okay. All right. Fine. So let's start our lecture for today. Thank you for coming online. And if ever you face any problem not hearing, etc., just let me know. So what we had done in last class was that we covered till the network address translation. All right. And what NAT was providing us, that NAT letting us use local network number addresses to connect to the internet. So in a way, the problem that we were facing, which was of running out of IP addresses, was somehow solved by NAT, because NAT was allowing us to join the internet even when we didn't have a globally unique IP address. Is there any doubt about that part? Okay, good. So now that the problem is kind of solved, do we still want a solution? Okay. So that is the first question that is asked. Well, I mean, that when IP addresses were running out, obviously it was made very clear that we need something, but we will still discuss some more details of it. So number one motivation of going to IPv6 was obviously that we will not have address space after some time. I mean, we are talking about many years back. This idea had already come that we are running out of spaces. So that was a motivation to bring IPv6. But then there were also some other motivations, because by the time internet came, it I mean, it was very clear that the initial aim of connecting computers over a network were very different than the way computers networks were being used. For example, there were many applications which had come, applications which, like video streaming, applications like the Zoom call that we are having. So many such applications had started coming in, which kind of indicated that internet will be used for many different uses than just data transfer. Okay. And that's why it was also assumed that, look, there may be a need into changing the basic protocols. So one of them was, for example, IP packet. As you know, the IPv4 packet. So IPv4 packet has a variable length header, if you remember that. And it is always time consuming to process a variable length header, because you have to first find out how long the header is, and then you have to process that many bytes of it. So, and IP layer, as you know, is also present on every machine. I mean, it is present on the core. Every machine has the IP layer. So one simple solution was that, hey, why don't we change it to a fixed length header? Okay. The second was what I was talking earlier, that applications started emerging which kind of had a flow into it. For example, like our case. Okay. So we had a flow. It is not just a data transfer that is happening, but data also has a meaning from what has was said before, after. There's a timing issue, there's an inter packet issue. So there are many such things which started emerging. So that's from the motivation for the IPv6, even though the original and initial motivation was addressed, but it was thought that if we are developing a new protocol, why not try to solve some other problems as well? So came the new IPv6 datagram format. We discussed it a little bit last time, but now we will discuss it more. Okay. So it has few things. Number one is version. Version we need because you need something to say whether it is IPv4 or whether it is IPv6. And tomorrow, who knows, maybe we will have another protocol. Then there is priority. Okay, again we have it, and now it was becoming clear that more and more applications will come which may have different priority levels. So no harm in having it. We also have a new field called flow label. Okay, so what does it indicate is that it is giving us an opportunity to define that the current set of processes which are going, they're part of a flow. Okay. Whether we use it or not is in our hand, but it gives us that opportunity. Okay. Then we have payload length. We have payload length. Okay. Header is fixed. Header is now 40 bytes, but payload could be variable. So we have a payload length variable. So as you see that to process header, we don't have to check the length. We just have to know the length, that how much of the data it is containing. Then it is next, means where would it go? It would go to TCP, UDP, where would it go? And hop limit, which is a kind of a number which says how many hops the packet would go before it dies. So hop limit, for example, if the hop limit is 8, then packet will be passed through the 8 intermediate routers and then it will die automatically whether it has reached the destination or not. Hop limit is done to make sure that packets which are lost, packets which are delayed, they eventually get cleaned out of the network and they don't just keep getting routed. Now you will also see there is no fragmentation, there is no checksum. Many of the things which were in IPv4 have been removed. Okay. Fragments were removed because fragments were creating a lot of problem. And I gave you an example in the class of a real problem that we faced in our team. But fragments were always very tricky. So fragments have been removed. Now tell me one thing. If I remove the fragment, but I receive a packet from my previous hop, which is too big to be sent to my next hop, what is the solution? What will I have to do? Earlier, I was solving this problem using fragments. Now, how will I solve it? You may raise your hand and then you can speak. Okay, Aditya, go ahead.
So I think we can set the payload length and the flow label that we have divided the packet into different parts.
No, how will you use that?
So we will set the payload length as the trimmed number of bytes we are sending. And then I
Fine, but
think we
how
can
will you?
set the flow label that this is part of the previous packet.
Okay, but how will you set the offset? There was also a field called offset.
So yes.
I mean, you can say that, okay, these two are part of the same flow. Number one, you have to also tell these two are part of the same flow means there could be other packets, but you are talking about single packet. Okay. Number two, you don't have an offset. Anyone else? Think of a logical solution. Okay, think of a logical solution. Logical solution is, let's say there are three people, you are in the middle, there is a person before you, there is a person after you. The person after you is maybe a slightly weaker person, younger person, and he can only carry, let's say, 20 kg weight. The person before you is really heavy, big person, and that person can carry an 80 kg load. Okay. Now he passes you the 80 kg load. Now you see you can also carry 80 kg, but you are seeing that the next person can only carry 20 kg. Earlier solution was you take this 80, divide it into four parts, and give 20 each to the next person. Now you cannot give it to the next person. So what are you going to do? Any intuition?
Maybe we can set the minimum payload length throughout the pipeline.
Okay, but that's fine. But then if the next person is also 80, then you are sending too much,
Hmm.
too
Hmm.
many unnecessarily. Yeah. But like
Yes,
even
yes.
in this situation, the same problem may still happen, right? Unless you have everything uniform, the same problem may still happen, and you cannot have uniform because you are on a network. What would you do in this particular situation? Just think of the real situation. Forget about network. Well, if I am in the middle, then I would say to the person before me is, hey, look, no, no, you can't give me 80 kg. You will have to give me 20 kg because I cannot pass 80 kg. So I will not accept 80 kg because I know I cannot pass 80 kg. So that's what IPv6 does, that it sends a control message to the previous host and saying packet is too big, divide it. I will not take it. And you can say that it can keep going back. I mean, it can keep going back to the initial one where sort of the problem originated, and because the problem originated from that part, that person would better make it a smaller packet. Otherwise, the packet will not pass through the network. Understood? So earlier, what we were doing is that if a host felt that the next link cannot afford that big packet, it was dividing it, setting the offset, sending the fragments. Now what it does is it discards the packet, sends a control message back to the previous host saying that the size which was sent was too big and needs to send a smaller packet. Anyway, now we cannot have the solution of having a uniform. I mean, we can, but we cannot guarantee using a uniform length is because then we will have to guarantee that each link between each router supports that minimum. Okay, and that is a very heavy restriction. Understood? Okay. All right. Yeah. Okay. Yeah. So Vikram Mantri did put the same answer on chat. So Vikram, you can also say it out loud, but that's good. Yeah, Aditya.
So how is the context set that the packet is divided and it should be combined at the end stage?
How's the?
How is the context set to the next person that there has been
No, so
fragmentation
the
done?
previous person is now not dividing the packet. Previous person is now creating smaller packets.
Okay, okay. And then can we have the next trend that the next person can handle more data? So will the length increase?
No. Basically, if
Okay,
you
okay,
have something in the middle, then the packet size is that
okay, okay.
bottleneck. Okay. Anyway, so now we move forward. The other two fields are self-evident. Source address 128 bits, destination address 128 bits. Now give me an answer using 128 bits. How many addresses can you have? Using 32 bits, you could have 4 billion addresses. Using 128 bits, how many addresses you can have? Don't give me 2 raised to the power answer. Give me a human number answer. Any guess?
It's a very big number.
Very big number. Yeah. Billions, trillions of numbers. Okay. So hopefully we will not run out addresses again. But you never know. Nowadays, almost everything is having an IP address. There are ideas like smart dust, drones, everything has it. So you never know. But for the time being, it looks like that now we have a really, really large number to cover. Okay, so this is the IPv6 datagram format. And nowadays, if you have bought a new laptop or a new phone, you would see both addresses in your machine. Okay, fine. So now we move forward. Now that comes to the second problem. So you have got a IPv6 format and you have got an IPv4 format. Okay. How will you move from IPv4 to IPv6? Think about it for like 10-15 seconds or 1 minute and then raise your hand and then I will call you one by one. Raise your hand once you have an idea that that's how we can switch. Anybody? Okay, so there could be multiple approaches, right? So one approach, for example, could be we say, okay, internet will be down tomorrow, and when we wake up, there will be IPv6. Okay, so something like when Europe changed from individual currencies to euros, that's what they did. You could do transaction one day back in local currency, and the next day, when you went to the ATM, took out the money, it was the euro coming out. Okay. Uh, Indian government tried something similar, but it failed miserably when they banned the 500 rupees note. Okay. So, do you think this will work? And if this works, then how could it work? Or if it doesn't, and if it doesn't work, then why it will not work? Yes, Kunal.
So I believe ki every computer has both IPv4 and IPv6. The only reason
Hmm.
is because current
Every
still we
new
have a lot of.
computer, Kunal, every new computer.
I think they still should have both. I mean, they are transitioning now, but a lot of applications are still running on IPv4.
Yeah, that's the problem, right? I mean, if everybody had IPv6, then you can switch. The problem is there are a lot of machines which only has IPv4.
Uh,
There are
so
lots of machines.
we let application layer or TCP/IP layer decide which should we prefer IPv6 or IPv4 depending upon the connection
No,
which we.
TCP layer cannot change it, right? I mean, if your machine doesn't have IPv6, so there are machines in between which do not have IPv6 address. They don't know what is IPv6.
Yes, we can just do a DNS lookup. If we get a, then we know ki it's IPv4. It's a quadruple A, then we know ki it's
Yeah, that's
IPv6.
fine. But suppose I have to send a packet and I have to send a packet through you to Aditya. Suppose we are three machines. Okay. Now now I don't have IPv6, or maybe you don't have IPv6, right? So if you don't have IPv6, it doesn't matter that I and Aditya have IPv6 or not.
Yes, sir.
Understand? So it's not always a choice of the machine to choose a format. It can only choose a format if it has both. But there are some machines, and when I say some, it means thousands of millions of machines which don't have both. Because, I mean, you would not believe, but mainframes are still running. COBOL is still being used. So you are on right track. You have to just think a little bit more.
So by default, we said that IPv4 is used, but if some machine is supported, then we can shift to IPv6. Like in here, we can set the version header to IPv6.
So you are saying by default IPv4 is used, but
Yes. For now, until we know that all machines have
okay,
IPv6
but that's
installed
a
with them.
very long process.
Hmm.
That's a like 40-50 years you are looking at. But your problem was very urgent. You wanted to have more addresses. So if you ran out of IPv4 addresses, you bought a new machine, it got IPv6. But you are saying I will not use it till everybody gets IPv4, till everybody gets IPv6, which is like a number one, it's not in your hand because you may change it your machines, but you can't change the machines of the internet. So Kunal, what you were saying earlier, can you think a little bit more on that?
I was also thinking if we have let's say if my machine doesn't have a IPv6, we can have something like a proxy server which contains an IPv6 server, address.
How?
Um, it I I mean, we can have a IP proxy server and we connect to the server which has an IPv6 address and it takes all the requests, it accepts all the requests coming from outside. And we
And
can
then,
just use IPv4 between the local connection between my CPU and the proxy server.
so every machine will have to have another machine which is IPv6.
I mean, it's not viable for every machine, but for large applications like for any company which is still on IPv4, I think this would work.
Yeah, but those companies will anyway most likely buy a new machine, right?
Or
Vikram,
like,
can you say it out loud?
Hello, hello, sir. Am I audible?
Yeah.
Yeah, so like, can we just like put the data of the IPv6 packet as like the payload of the IPv4?
Okay. So can you elaborate that?
Like for example, let's say the situation that first device is IPv6, then the intermediate device only supports IPv4, and then the last device supports IPv6. So like if we wrap our data as like the IPv4 payload, then the intermediate device can also like somehow manage that. Like we should be able to implement it, maybe.
Hmm. Okay. So basically, what Vikram is saying is that I will send. So Kunal, this is also what you were also trying to say. Suppose there are three machines. Okay. A, B, C, and let's also make D, and let's also make whatever alpha over here. Suppose V is IPv4 and rest of the machines are both. They have both. Okay. Because any machine that has IPv6 also has IPv4, right? Now the challenge to us is that if alpha sends to A, should alpha use IPv4 or should alpha use IPv6? And one solution like which was being suggested that we wait for all machines to become IPv6. In that case, even though the 4 out of 5 machines are IPv6, they will still use IPv4. That's a solution which is a valid solution, but it has a long path. Long path means, for example, if government tomorrow says everybody switch to EV, it means that till the deadline happens for all diesel petrol vehicles will start running. Okay, fine. So it has a long path, but that is one solution. That's a valid solution that everybody uses IPv4 till everybody becomes IPv6. The second solution that is there is that alpha is directly connected to A. So alpha can always know what is the capability of A. Alpha doesn't know capability of B, but alpha knows capability of A. Okay. Now alpha knows that A can do IPv6. So alpha will send to IPv6 a packet as an IPv6 packet. But when A looks at it and A says, hey, it needs to go to B and B can't handle IPv6 packet. So what A will do is A will create an IPv4 packet, and suppose this was the packet of alpha. A will create an IPv4 packet, and in that packet, it will put the IPv6 packet. So in the payload of the IPv4 packet, it will put the entire IPv6 packet. Okay. Imagine C is also v4. Okay. Now this IPv4 packet reached B. B will read IPv4 header, pass it to C as IPv4 packet. No challenge. C is also only IPv4 or IPv6. It could be anything, doesn't matter. But let's say IPv4. C will continue to pass this IPv4 packet. Then it reaches D, and let's assume there is also an E, which is also a new machine. So both D and E are IPv6 machines. So from B to C were IPv4. So B to C, this IPv4 message will go, which inside has an IPv6 message. Now, when C passes to D, C will still pass to D an IPv4 message because C's capability is only IPv4, but D is capable of both. So when D gets the IPv4 message, it finds out that in the payload of the IPv4 message, there is an IPv6 message, and the next link from me can support IPv6 message. So it throws the wrap away and sends the IPv6 message to E. Any doubt? Clear to everyone?
Sir, could you repeat once?
Okay, so let me repeat. Let me try to find out something better. Okay, suppose we have few machines. Machine A is V6 compatible. Machine B is V6 compatible. Machine C is only V4 compatible. Machine D is only V4 compatible. Machine E is V6 compatible. Machine F is V6 compatible. All right. Now A has to send a message to F. Solution number one, not every device is IPv4, therefore not every device is IPv6, therefore we will send IPv4 only. Perfect solution, works but does not use the power of IPv6. Okay. Second solution is A to B, the message will be an IPv6 message. B will receive an IPv6 message, but B knows the capability of C because B is a direct neighbor of C. Okay, so at some point of time they talked and C said, hey man, I'm still IPv4. Okay. Now we knows that C cannot handle an IPv6 message. So what we will do is B will create, let's say this red message is the IPv6 message. So B will create a IPv4 message, the blue message is IPv4 message, and put this red message as the payload of IPv4 message. Okay, it goes to C. C can handle IPv4, no challenge. C then sends to D the same message that it has received, which is nothing but a wrapper of an IPv6 message. D sends to E the same message that it received, which is a inside an IPv4 message. Okay. C got it. Now E needs to send it to F, but E knows that F can handle IPv6. So E will throw the wrapper away and he will just send a IPv6 message to F. So if we use this, then we can implement IPv6 right away. We will not have to wait for each device to become IPv6 first. Okay, because the new devices are capable of new as well as the old, so they can accommodate the older device by converting to IPv4 format, not converting, by wrapping with IPv4 format whenever it is needed. Clear? Now I have one question. Okay, it is your time to ask any doubt, otherwise I will ask a question. Okay, so my question is that 6 may also be connected to, let's say, some other machine, let's say P, where P is a IPv4 machine. So P may also send to E a pure IPv4 message. pure IPv4 message means it is IPv4. There is no IPv6 inside it. It is IPv4. Among these two messages which come to E, how would the E know that in one of the message there is an IPv6 message underneath and another message it is just an IPv4 message? How would it know that?
So you can have some flags hidden in the options variable, options header in the IPv4.
Very good. That's the answer. So we had the flag bits, we had the options in the IPv4 that is used to indicate that whether the payload is a normal payload or whether the payload is a IPv6 packet. So using those flag bits and options bit, a router can know whether I am handling a regular IPv4 packet or I am handling an IPv4 which has an IPv6 inside it. Any doubt to anybody? Okay. So that's good. I think you have got it right. The technical term for this thing is called tunneling. So you tunnel the IPv6 datagram into an IPv4 datagram and you send it. Okay. And you can see these nice animations, but typically what happens is what I told you. So you see this bottom image. So this is what we were telling. So IPv6 at the two end can still use the IPv6 fast processing flow, whatever, but they can still use of IPv4 routers in between, and you can start the deployment of the protocol right away. You don't have to wait for each device to upgrade. Okay. So this is typically a better idea instead of drastic changes. For example, I mean, again, the real life example is the currency change. Currency notes have changed multiple times, but they were done gradually. They just introduced new notes, older one went away. When you want to make a sudden change, you either have done a lot of preparation or you end up sort of messing up the entire system. So IPv4 is kind of doing a gradual transmission. Gradual transmission means it has started using slowly all what it can use as IPv6. If not, then it uses IPv4. Okay. Now this is a 2023 report, but still you can see that almost 40% of the devices are now IPv6, which means that still 60% of devices are not IPv6. And NIST, which is the US government agency, is saying that only one third is currently IPv6. So like two-thirds is still not IPv6. Okay. So it will take some time. It will take easily 20 more years maybe from now onward to become a complete IPv6 network. But yes, that's what we have. So things change very slow. Okay. Long time to deployment use, because if something is working, nobody changes it. Okay. Now we will just go through some slides just for your knowledge. But what I have covered till so far, that is the part of the syllabus. What I am going to cover now is just to show you few things, but not really a part of syllabus. SDN is not, we will not cover anything about SDN in the as like in the curriculum for exams, but just giving you a basic idea. Okay. So we have been talking about forwarding table, etc., and we have been talking about IP address as a logical address which can help us implement things. So next, some examples are giving you how we use it. Okay. So number one, there are multiple things. I mean, these slides I will upload. But what I want to show you is that these are the type of forwarding table that you have. So you can have like the first entry. First entry here is that coming from any source, but going to this subnet, forward it to line 2. Coming from source, this particular one, from this particular subnet, no matter where it is going, drop. So what it is doing is it is blocking this traffic. Okay. again, coming from a particular source, no matter where it is going, analyze this packet. Okay. So these are the things that you can put into your router or your gateway router, and then you can manipulate the packets as you want. You can also see uh, hmm. So these are like the OpenFlow is a new open system. I mean, it is open source. That's why it is called OpenFlow. So here you will see the first line. Okay. So this is, we are currently not covering. This is the link layer. We are only trying to see this one in IP and network. So if you see, these are some entries. For example, it says IP destination is this, action port 6. So if the packet, no matter where it is coming from, if it is going to this, it should be sent to port 6. Okay. It may be a very important IP. It may be an IP for which you want to provide certain service, and that's why for that IP you have an entry that if the data is going to this IP, then it is port 6, and port 6 may be kept free from all the other ports, so it minimizes the loss, for example. Okay. So this is like one way of implementing some quality of service. Then there are some examples of firewall here. For example, no matter where the packet, if you see the second entry, this one, no matter where the packet is coming from, asterisk, asterisk, asterisk means that, but if the destination port is 22, then the action is drop, means it is not letting any packet directed to 22 port come into the system. Okay. The another example is, if you want to block a host, for example, if I want to block your machine so that you cannot access internet, rest of the classmates can access internet. So for example, let's say this is the machine address of let's say Aditya. So I don't want Aditya to access internet. So I will just set a rule like this, that if the source is this, then no matter where he is surfing, all packets drop, and then his internet is gone. Okay. So these are just some examples of how the forwarding table entries look like. And now, I mean, you can ask even more example on internet, but this is just to give you some idea. So basically, using forwarding table, you can actually decide. I mean, forwarding table is like your traffic police person, right? So you can say left, right, stop, and as you can see, the traffic police person can hold one line much more longer than the other line, etc. So they can introduce some quality into the system if they want to. So you can go through these again, but I just wanted to give you a small example. Again, the initial idea of IP network was that IP is IP layer, because the IP layer has to be, on all machines. The initial idea was that the IP layer should be very lean, means there should not be too many things at the IP layer because it needs to do a lot of work anyway, and it is on all machines. So that is what we used to call IP layer as a IP hourglass. So IP had a thin waist. Okay. However, what happened is that because of the way network grew, you ended up having NAT, you ended up having firewalls, you ended up having load balancers. How many of you know understand load balancers? What is a load balancer?
A load balancer is like it distributed the load between multiple servers.
Yeah, so for example, when you type google.com, it is not one google.com server. Okay, so what load balancer does is that it distributes the queries to different servers so that different server answer your queries. I mean, maybe the day Google started, it only had one server, but as it grew, it implemented lot of servers which will all serve to the google.com. Caches, we already covered what are caches, right? So what happened is that the initial idea was to have an IP as a very thin layer, means do very small thing and do it more efficiently. But we ended up having lot of things embedded into IP. And NAT, for example, is there only because the IP addressing was an issue. So one of the reason that, you have a lot of arguments against and for NAT, but one argument against NAT is that it is adding extra work for the IP layer, which it should not. What could be a pro argument for NAT, by the way? Any pro argument for NAT? For NAT? Anything good about NAT?
We can have multiple devices having internet connection with
Besides
only
that,
one public
besides that,
IP address.
besides that, suppose I have enough
Yeah.
IP addresses, would NAT still help?
Yes, it will help on the server side, I think. It will receive only a request from one host if we consider an organization.
I
We
can't
can
quite
consider a
understand.
reduced load.
No, that I
Maybe,
can't understand what you're trying to say.
maybe it can help like to sort of implement things within an organization. For example, blocking certain IPs or controlling stuff like that.
Exactly. So even though NAT was originally designed to handle the address scarcity problem, it turned out that it is extremely helpful for maintaining security and policies like if you want to block something or if you want to do something, because then your gateway routers could very easily do that. So whether NAT will remain if we get all IPv6 or whether NAT will go away, we don't know. Most likely it will remain. Okay, so currently what happened is, I just wanted to show you one more image. Yeah, so this is a good image. So initially we started with the telephone network, and the telephone network was designed in such a way that the endpoints were dumb terminals. Okay, they didn't do anything, and all the intelligence was in the network. Okay, so the making a call or receiving a call was at the end level was a very basic electrical operation. There was nothing specific into it. Then we came to the internet, and internet was designed with a very different ideology. And internet put all the intelligence at the end systems because they were also computers. And then it made a very basic network in between, like no frill service, best effort service, etc. Nothing to be done. Okay. So it had an advantage because it made it grew very fast. Now what we have internet is that we have intelligence at the end, it remained, but now we are also putting intelligence into the core of the network via SDN, software defined networking. Okay. So we are also now making the core intelligent as well. So for example, earlier the ideas of security especially was that it is the host, it is the end node's responsibility to handle the security. Now we are trying to say, can the core also handle the security? Okay. So maybe the core can stop the malicious traffic rather than the end have to deal with it. So some of you may have heard of the attack called DDoS. Okay. DDoS, anybody will give full form?
Distributed denial of service.
Yeah, distributed denial of service. Okay, so distributed denial of service is that you have a single server and different clients just start accessing your website, for example. But they access so much that a genuine client is not able to access it because their queries or their requests have piled up here, right? So imagine you are going to buy a ticket, you are actually going to buy a ticket, but then there are like hundreds people who come and who just want to ask a question, and their questions are not genuine, but they just want to deny you to buy a ticket. So they just are ahead of you. Okay, so this is the denial of service. And traditionally, like even today, the denial of service, to handle denial of service, is at the end system. But the idea, one of the ideas of putting intelligence within the network is, can the network see, hey, this is a DDoS attack happening, and let me start dropping packet before they even reach the end system. Okay, so this is what we mean by putting intelligence into the core. It's happening, it will take some time, but that's what the idea is, that let's also make the core intelligent. Okay, so now network layer per se is done, and this is what your syllabus will be. Okay, for the questions for the paper and exams and quizzes, etc. Now we come to the interesting part, which is that how do these forwarding tables that we were using, how do they actually get built? Now this part is both interesting, but thankfully you have already covered this part in your algorithms course. So hopefully we should be able to go through it pretty quickly. Okay, and you can look at these slides on your own, but like it shows the IP fragmentation and assembly, or maybe let me just show you an example. Yeah, so that's how currently IPv4 fragmentation and assembly happen. Send 4000 bytes, maximum can be sent as 1500. So it will get 4000 bytes, so it will get 1500 is length, but 1500, the 20 byte will be header, so only 1480 bytes of data it can send. Offset is 0. Then from 1480, and the offset is count in terms of the 8 words, so that's what divided by 8. And then it says another 1500, and then it says 1040. Okay, so that it can send it the entire packet. So it divides and it sends. Fragmentation flag set 1 1, and then 0 means no more fragmentation is going to happen, and id is remains same. So it knows, so when it receives the 3, it searches for all 3, same id, fragmentation flag, and by offset it reassembles the packet. The tricky part obviously in fragmentation was that suppose the middle one is lost. If the middle one is lost, then even though these two have reached, it is of no use. Okay, so the fragments created their own problem, that if any fragment gets lost, then the entire, all the fragments have to be discarded. That's why instead of the fragment, the new idea in IPv6 is that let's create a smaller datagrams to be sent, rather than taking a bigger datagram and then fragmenting it. Okay, so but fragmentation now, as you can see, is on its way out. All right, DHCP we covered last time. We also showed you on the Wireshark, so I will not cover this. So that's for the data plane of the network layer. Now we are moving to the control plane of the network layer. So that is the chapter 5 of the book. Okay. All right. So now we start with how the question that we have is that how does the forwarding table gets built in? Okay. So you studied algorithms, and in your algorithms course, you studied some graph algorithms. So which graph algorithms did you study? Anybody? Algorithm course, all of you have taken, right? Algorithm is mandatory for you?
Yes, sir.
Yes, sir.
Okay. Okay. So Okay, if you don't remember, don't worry, we will cover it. So anyway, so what we are seeing is that we need to find out how to go from point A to B, and we want to figure out the way to do that. Okay. So I will not cover these initial slides. I mean, we have already covered in SDN, etc. Now we'll come to the main problem. So the main problem is that from this machine, I have to go to this machine, and there are different nodes. Where do I go? So if I am at Triple IT Delhi and I have to go to, let's say, Connaught Place, then which road should I take? Okay, that's the problem. This problem is not new. Problem has been there. Human have solved it for the regular path, and algorithms have also solved it. But we have to solve it for the network. So our goal is to determine good paths from sending host to receiving host through network of routers. The word good here is important. Okay. But as we will see, what good means will vary. Path is what? Path is a sequence of routers packets traversed from given initial source to the final destination. So that's our path. Why do we need path? Because at our IP layer, the host sends message to the another machine. Okay. So they cannot directly send to this one. They have to send it to the another machine, and they may be connected to different machines. So your packet need to know to go here or here or here. Okay. So that's what we mean by path. All right. Now let's also look at the good part a little bit. So the good part could be minimum cost. Good part, what is the cost? Cost is again a very abstract terms in terms of the language, but you can say cost could be like for example, if Airtel charges some money and Vodafone charges another money, then the cost could also be financial cost. Okay. Cost could also be translated into in terms of time. If it takes longer time, then you can say it is a costly path, or I mean, though we have the term fastest or slowest. Cost could also be congestion, that if there is congestion or not, probability of dropping, etc., etc. So you could have a financial cost, you could have a time cost, you could have a congestion cost, and all of these in some abstract way defines what your good path is. For example, if you have to go to CP, how will you go from Triple IT Delhi to CP? Okay, anybody who goes to CP from Triple IT Delhi can say. How do you go? Anyone? Okay, so when I have to go, I can take two routes. One, I can take the Mathura road and drive straight. Two, I can go into the middle, somewhere around Nehru Place, and going forward from Nehru Place, East Kailash, and so on, and then I can drive through. Another, I can go towards Ames, through IIT Delhi, Ames, and then I can drive through. Okay, so there are multiple ways I can reach CP from Triple IT Delhi. I have to find one of these paths. Mathura Road, for example, may be offering me a much more straighter route, a smaller route. Okay, so my petrol cost, the financial cost of petrol is less, but maybe the road that is going from through Ames is least congested, as such it is reverse, but let's assume then that may be offering me a least congested path, and so there is a less probability of dropping. And then there could be this path somewhere in between through east of Kailash, which may be a super highway, and that may be the fastest path. Okay, so the good will vary, and therefore the routing still remains a challenging network problem. Okay, you can still always find a good routing algorithms. Fine. So that is for the motivation to you. Now let's move to the next thing. So what we do is that to solve this, and as people in algorithm taught us, we try to abstract it out as a graph. And a graph is defined in terms of nodes and in terms of edges. Okay. So you can see, you can imagine these point as routers, and or these points as destinations. Okay, it's up to you. But let's assume that these are all routers for the time being, and we are going from a router to another router. So the graph G is given as node and edges. So in this case, our N is U, V, X, W, Y, Z, and our edges are the lines that are drawn here. So the edges are UV, UX, VX, VW, etc., etc. So we have certain edges, and we may not have certain edges. For example, we may also have an edge like this, but currently we don't have this, right? So that's fine. Now, each edge, we will associate a cost to it to do our calculation. Okay. Where is this cost coming? Like we go to the previous discussion, that this cost may be calculated as a actual financial cost. This cost may be calculated as some form of congestion, some form of link speed, etc., etc. We are not currently not bothered about it. What we are bothered about is that if there is a cost given, and in a simplest case, you can always say that the cost from one hop to another hop is one. Okay, but if there is a cost given, what is the least cost path that we can find? Okay, and then we leave the calculation of cost to some other entity. Now, considering this problem, that how do we find out the least cost path, there are different methods or different realities when it comes to the computer network that needed to be taken into account. And that's where the network becomes little different than what you have studied in algorithms, because algorithms you study theoretically. Network you have to also see how to implement it practically. Okay. So the things that we will have to take care of is our algorithm global in nature? Global in nature means, does all routers means all routers of the network have complete topology, means they know exactly from A to B how to go. And this is called link state. In other words, also Dijkstra's algorithm, because Dijkstra designed it. The another approach could be, I only know the cost of reaching my neighbor. So I only know that my neighbors are Kunal and Aditya. Okay, that's it. So I only know the cost of reaching my neighbor. Then through my neighbor, I iteratively calculate cost to each other. So this is more decentralized. Okay. So I'm only worried about my own path to my neighbors, and then I am iteratively calculating path to the others. The other consideration which you will have to take into account is, how fast do routes change? Okay. Do you need to run the algorithm very frequently? So if paths are changing very frequently, then ideally you should be running the algorithms very frequently. Or do you need to run the algorithms slowly? Okay, so if nothing changes, for example, if no links are changing, link speeds are same, traffic is same, then maybe you need not to change or recalculate your paths. The way I will say a human analogy is that when there is low traffic, let's say on Sunday, then roughly all the routes that you see remain kind of same. However, if there is an event, for example, if there is a Diwali Mela or other Shahra Mela, whatever, then you will see that some routes get congested very quickly, and then the people start moving into another routes and another routes, etc. So in those cases, basically the route dynamics are changing very quickly. Okay, so you may find that the main road is empty, but there is a lot of traffic in the side roads, or the other way around, right? So these are the same things that you have to keep in mind with respect to the computer network, that are routes changing slowly, are routes changing quickly. Do we need to have an algorithm which has a complete information about all the network? Do we need to have an algorithm which has only information about its neighbors? Okay. Now let us first study the first algorithm, which is also a very old algorithm, link state. Okay. Uh, all right. So it is Dijkstra's algorithm. So it is very old, as you can see, it still works. So Dijkstra's algorithm is a centralized algorithm. Centralized algorithm means network topology, link cost known to all nodes. How does it work? It works by broadcasting. What is broadcasting? Like I said, in network, if you send a packet which reaches all other packets, then we call it broadcast. There's another term which is called multicast. Have you heard of it? Anybody? We used this term when we were giving introduction of TCP. So TCP is what we called was unicast. It was not multicast. Multicast means that if there is a network, broadcast means if it sends packet, it goes to all. That is broadcast. Multicast means that if it sends packet, then it goes to, let's say, only to this, and this. Now this three, so one packet goes to three, this is multicast. Packet goes to everyone, that is broadcast. Okay. Anyway. Just a second. I want it to update. Yeah. Okay. So what Dicastar does is that it computes least cost path from one node to all other nodes, and that running that algorithm gives the forwarding table for that node. Okay. Now we are first going to use some notations, see through an example, and then come back to the algorithm analysis. First is that from node X to let me just write here because it's the control goes away. So if I have these nodes, this is my X, this is Y, this is Z, then this link cost is what I am calling as CXY. That is the direct link cost. 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 That is the direct The dV is the current estimate of cost of least cost path from source to destination V. Now my destination could be anything. Okay, so there may be another network over here which is W, and my destination could be W. So what dV is saying that for X, what is the value of dW? So that is what the dV is. PV is the predecessor node along path from source to V. So PV basically says what is a predecessor node from source to V. So W access to reach the predecessor would be Y. N dash N dash is the set of nodes whose least cost path definitely known. So in the beginning, when we will start the algorithm, the N dash would be empty. Okay. And at the end of the algorithm, the N dash should be equal to all the routers that are present or all the nodes that are present into the graph. Any doubt about any of these notations? All right. Now let's look at the algorithm first. So what the algorithm does is n dash equal to u. So u is what is starting, means I am calculating for u. So I definitely know that the cost of reaching me by myself is 0. So I know that. So I have got that into the n dash, because n dash is the set of nodes for which the cost is, the least cost path is definitely known. So I only know about u. So that is what I have got here. Okay. Now for all nodes V, okay, just like V is a variable. If V is adjacent to U, means if V is the direct neighbor of U. So U, and let's say 1, 2, 3. And then we have 5. And then we have 6. So the direct neighbors are 1, 2, 3. Okay, not 5 and 6 are not direct neighbors of U. So if V is adjacent to U, then what is the cost of reaching V is equivalent to the cost of the link. So idea is that to your neighbor, your immediate neighbor, which is your adjacent, the cost to reach is equivalent to whatever the cost is in between you. Okay. For reaching from U to 5, it will be the sum of this cost and that cost. But to reach 1, the cost will be the cost of this link. So that is what this line says. Then dV equal to CUV. If the node is not adjacent to you, okay, means if it is not an immediate neighbor, then dV equal to infinite. So currently what it is saying is that it is initializing. And in the initialization phase, what it does is that immediate neighbor, it sets the cost as the link cost. And for each other node into the network, it sets the cost as the infinity. And our purpose of running this algorithm would be that this infinity changes to some finite number at the end of the algorithm, and possibly the optimal finite number. Okay, so that's the initialization phase. And then comes the path, the process of calculating this path for each node. Okay, now let's see the loop. First line is find W not in N dash such that DW is minimum. Okay, so let me go to the next slide. So this is the graph. Okay, so in this graph we are starting from U. U has how many neighbors? U has 3 adjacent neighbors. V, X, and W. So V, X and W, these are adjacent neighbors. For the adjacent neighbors, we will initialize it to the cost of the link. Okay. So the cost of the link is to V, it is 2. To W, it is 5. This is the 5. And to X, this is 1. So that's what I have written. 2, 5, 1. And then I have also written a predecessor node. So predecessor node in all these cases will be U itself. All right. So this first line is clear. And then the Y and the Z, which are not directly connected, it is infinity. So this is the initialization phase. Then the next line in the algorithm says find W not in n dash such that DW is minimum. So in this, which D is minimum? So I find that the dx is minimum. Okay, dx is 1. So this is the minimum. So I go back and I say, okay, so the dx is minimum. Add w to n dash means bring x to the final set, and update dv for all v adjacent to w and not in n dash. Update dv for all v adjacent to w means we are talking about neighbors of w which are not currently in the n dash. So n dash, so far there was only u and now there is x. So nothing else is in the n dash set, right? So now we have to update that. Now x, as we see, x has neighbors. X has got y as a neighbor, which was earlier you was not even aware of. And even w is a neighbor of x and v is a neighbor of x. So we will do the updation. How do we update? We take the minimum of two numbers. One number is our original number and the another number is our sum of the link plus the new cost. So if you see dv equal to, so dv equal to, v is this v, minimum of dv, that is it is reaching direct, plus minimum of u going to x and then from x it is going to v. So dx plus cxv. So the first value is 2, second value is 1 plus 2. Okay, so 2 and 1 plus 2. 1 plus 2 is 3. So the minimum of 2 and 3 is 2. So nothing changed. Okay. For W, the cost is dW. dW was 5. Okay. And then the new cost is through x, that is u to x and then x to w. That is 1 plus 3, which is 4. Now this one got modified because we initially had 5, but now we will get 4 hopefully. And then dy. So dy's initial cost was infinity, but now we can reach dy through x and the cost reduced to 2. So let's see the next row. Here it is. Okay. Any doubt in anybody's mind? It's a very simple calculation. No challenge at all. We follow the same thing again and again. After x, we will pick one among the u and w. Okay. Oh, sorry, u, w and y has also now come. Now the minimum is v and y and w. So minimum is y or v. We can pick anybody. So we have picked y as a random. We could have also picked v. So that doesn't make a difference. Then we do the calculation. Then next loop happens. This time the minimum is v. Then we do the calculation. Then w. Then z. By this time, we have calculated the path of all the neighbors. It took 5 steps to find path of all the neighbors. Okay. So after each iteration, it finds path of that many neighbors as the minimum path. Okay. So after one iteration, it found the minimum path to x. After two iterations, it found minimum path to x and y. After third iteration, it found x, y, v. After fourth iteration, it found minimum path for 4. After fifth iteration, it found minimum path of all the 4 neighbors. Now what we have got is, this is the path, or this is the least cost path tree from u that we have got. Now if you need to send it to z, then you knows that it has to send it to v. It has to send it to x and not to the v. Now it knows that. Okay. And this is the forwarding table in u. So if the destination is v, uv is the link. If destination is x, ux is the link. In fact, for most of the destinations, the outgoing link is ux, and that gives us the forwarding table for the u. Understood? Any doubt? You can go through this another example on your own. Okay, it goes through the same way. And then tomorrow we will slightly look into the complexity of the algorithms, and then we'll move to the distance vector. But today we are ending here with the introduction of Dijkstra. If there's some doubt, we can cover it next time. You can let us know. But otherwise, this is same as you studied in the algorithms, and we will not go too much into the algorithm complexity, etc., that you may have already covered. We will just see it from network angle, not from an algorithmic angle. Okay. Any doubt? All right. So we are now ending today's class. Once the recording is available, I will post it, and we'll meet tomorrow. Tomorrow, I think India time is 6 p.m., right? So that's what we will meet. Okay. Okay. Thank you, everyone.
Recording stopped.